Good afternoon. Good afternoon, everyone. Welcome, all of you. Thank you so much for joining in today. Today is day 4 of our training. And it's good to see that the number is still rising. So you're most welcome to day 4 of the Advanced Statistics and Experimental Design Training, which is brought to you by the World Bank through the Centers of Excellency in Agri-Food Systems and Nutrition at Eduardo Mondlane in Mozambique. So please, thank you once again. Thank you so much for continuing to participate through the training. And we want to thank our facilitators who are always here with us on time and taking us through the entire afternoon. Thank you so much, Professor and your team. So as usual, please, let's go on with the training. Participants, please mind of the time. If you are given the chance to ask a question or show the screen, please take as much short time as possible. And most importantly, please do listen to the training so that you don't ask questions which have been already given the answers during the training. So the certificate, please, we do not want to see the questions of the certificates again. Once again, I'm reminding you, we are going to work on them. And do ensure that you fill in the registration in the attendance registration form, which is going to be shared in the chats and also in the Q&A when requested. So please enjoy the training and all the best. Thank you. Professor Susan, I hand over to you.
Good morning. Good morning, everybody. Yes, here I am. Good morning, everybody. How are you? I hope everybody is okay and we are ready for day 4. Today we'll have a little practical and then we do our R practice. And we hope that if I can finish in the 4 hours, then my colleague tomorrow will be doing something on survey and categorical data analysis. So let's start. We will start from where we ended yesterday. We'll complete the theory and then run to practical. So I'm going to share what I had yesterday and then okay. So as a recap, yesterday we talked about simple linear regression. We said that it is a relationship between one response and one independent variable. We also say that the objective of regression is to identify the relationship to estimate the prediction. We talked about the assumptions under regression, and the assumptions included the response being normally distributed with mean mu and constant variance sigma squared, the residuals, the all unexplained variation are assumed to be normally distributed with the mean 0 and constant variance. We also assume the unexplained variations or errors are independent. They are normally distributed. We also assume that there is linear relationship between the response and the independent variables. So those are the assumptions that we looked at. And we looked at how we can test and see whether our model does not violate those assumptions. We talked about the residual plots. And one of the plots we talked about was the QQ plot or normal probability plot or a histogram of residuals. And if it turns out to be a bell-shaped curve, then we know that the assumption of normality of residuals is not violated. Anything that deviates from normality shows us that our data is not normally distributed. Then we also talked about a graph of residuals versus fitted values, and we say the mean of residuals, then we know that the assumption of constant variance is not violated. We also talked about independence. The errors or unexplained variation should be independent, not correlated. And we can always test that using a graph of residual versus time order or order of observations. And in case we don't get a graph which has a sort of like a sigmoid curve or a curve that has troughs and peaks. So if that doesn't appear in the graph, then we know that we have independence in our residuals. And we say that in case you find that you have non-constant variance, you can use natural logarithm, you log transform your response, and then run the regression again. On the other hand, you can apply the cubic terms or quadratic terms onto the independent variable to correct non-normality too. We also talked about including time as a factor in your model to account for independence of I'm muted. It's not on PowerPoint. I need to share.
Slideshow.
Oh, slideshow. Should be this one, I think.
Yeah.
Okay. Okay, so then we also talked about, I'm doing just a recap and then we are going to start with multiple regression. Saying that we also talked about including time. In case you find that you have residuals that are correlated, we can include time in the model and see whether that problem is solved. If it's not solved, we use time series. And that one is a big topic on its own. And if that doesn't solve, then we go for mixed models, whereby we will specify the correlation covariance matrix in the data to solve that problem. So there are various problems, but all those problems, you must be knowing them. You must have done something on time series. You must have learned what mixed models is. We are not going to talk about mixed model today or time series, but with time, we will be organizing those training online as time and funding allows. Okay, so today we are going to look at multiple regression. And I said that when you have a lot of unexplained variation, meaning that your R squared is small, maybe, for example, it is 30%. So meaning that in the response, only 30% of the variability has been explained. That implies that there are other variables, other factors that you need to include in the model. And if you do so, then you will have a regression between one response and more than two predictors or independent variables. And that is called multiple regression. And the regression model appears like this. This is when we assume that one model fits all these independent variables, depending also what you see in the scatter diagram. Remember that when you're doing regression, the descriptive statistics you do is to construct a scatter diagram and also produce some correlation. So those aid you to know whether you need two lines or different lines or parallel lines for your analysis. So here we find that yi is the response, and then x1, x2 are independent variables, while beta naught, beta 1, beta 2 Those are unknown parameters, beta naught being the intercept, beta 1, beta 2 are the slopes corresponding to each independent variable. We also say that the assumptions under simple linear regression still hold under multiple regression. And then we include one assumption. We assume that the independent variables are not correlated. That's why you see x1, x2 are independent variables. So they should not be correlated. Okay. An example of a regression between volume, diameter, and height. So when you get the output, you will get what we call the coefficients, the values of the coefficient. Here, the constant represents the intercept, and the value corresponding to diameter is the slope for diameter, and then the slope for height. And I yesterday said that when we are interpreting a multiple regression model, we hold one variable constant and interpret one. So if you have like 4, hold 3 constant, interpret 1. Then after that, you hold another 3 constant, interpret 1, and still you finish. So in this case, if we hold height constant, we are going to interpret the slope corresponding to diameter. And in this case, for every increment in diameter, volume increases by 4.71. If this was negative, if the slope had a negative sign, we would say that for every unit increment in diameter, volume decreases by that 4.71. But in this case, it is positive. So as diameter increases by a unit, volume increases by 4.71. So now, after that, we hold diameter constant and interpret height. So for every unit increment in height, volume increases by 0.339 cubic meter. So that's the interpretation of the model. So for your projects, you will not have volume or diameter or height. It depends on your objective. So you also interpret the model depending on the parameters, the variables you have in your project. Okay, down here we have a table consisting of the coefficient, the standard deviation, the t-value, and the p-value. Now, the t-value here, for example, minus 6.71, is a ratio of the coefficient minus 57.988 divided by 8.638. So this t-value is the ratio of the coefficient and the standard deviation. And then the p-value, using mathematical formula, we can calculate the p-value for minus 6.71. So here we are interested in the slope of diameter and height. So when we look at the slope, it has a p-value of 0.000. And we are going to use a significance level of 5%. This significance level is the probability associated with the null hypothesis. So the null hypothesis says that there is no linear relationship between volume and diameter. So for that null to be correct, our p-value should be equal to 0.05 or greater. So in case you have a p-value less than 0.05, we have evidence to reject the null and conclude that there is significant linear relationship between volume and diameter. So then we go to height. We find that also the p-value is small. It is 0.014. It is smaller than 0.05. So we have evidence to reject the null and conclude that there is a significant linear relationship between volume and height. Then when we have a value here, which is the standard deviation of all the data, we have our R squared. But remember, when we are dealing with multiple regression, we will interpret R squared adjust. Why? It has adjusted for all the parameters in the model. So here, our R squared adjust is 94.4%, it implies that 94.4% of the variation in volume has been explained by the regression model. So if you have any R squared adjust greater than 70, some books say greater than 70, other books say a range of 65 onwards. So depending on the book you're reading, you quote the book as you interpret your results. So in this case, we'll use 70%, although the book is, I can't remember it offhand. So we say that our model fits the data because we've explained 94.4% of the variability in volume. Okay. So there's also an analysis of variance table. And yesterday we looked at analysis of variance table when we have one independent variable. And let us focus on degrees of freedom. Yesterday, our degrees of freedom for regression here was 1 when we have simple linear regression. And we said the degrees of freedom when we have for any regression analysis, it is equal to number of parameters minus 1. In a simple linear regression, we have only 2 parameters, minus 1, we get 1 degree of freedom. In a multiple regression, depending on the number of independent variables, number of parameters go hand in hand with the number of independent variables in the model. In this case, we have 3 parameters, the intercept and 2 slopes corresponding to 2 independent variables. So minus 1, we get 2. Or the degrees of freedom again is equal to the number of independent variables in the model. Here we have volume, and volume has been regressed on to diameter and height. So we have 2 independent variables. Then the residual is equal to the total number of observations minus the number of parameters. And the total degrees of freedom is equal to n minus 1. So in this case, n minus 1 is equal to 30. If you make n the subject, n is equal to 30 plus 1, giving us 31. Those are the total number of observations. So minus 3 gives us 28. So that is degrees of freedom. Sums of squares, there is a formula. And then mean square, I said it is the ratio of the regression sums of squares and degrees of freedom corresponding to regression. We get the mean square, this one here. Then for residual mean square, it is this value here, divide with this one, 28. You get 15.1. And if you have a calculator and you get the square root of 15.1, it gives you the standard deviation that we saw of 3 point something. The F value is the ratio of these two, the mean square regression divided by the residual mean square gives us the F ratio. Then the P value, it is also testing the same hypothesis that the null is that there is no linear relationship between volume, diameter, and height. And the alternative is that there is a linear relationship between volume, diameter, and height. Since our P value is smaller than 0.05, we have evidence to reject the null and conclude that there is a significant linear relationship between volume, diameter, and height. Down here, we have what we call sequential sums of squares. It shows you the contribution of each of the independent variable towards the total, towards the regression sums of squares. I beg your pardon. So this value here, the regression sums of squares, when you add these two, you get this value, the regression sums of squares of 7,684.2. So if we add here, we are going to get 7,684.2. So 0.2. So that gives us the total sequential sums of squares. Now we can see that in explaining the variability in volume, diameter is doing a big job. You can see the amount of variability explained, and height is also doing some good job. Now, when we are doing model building, we look at the contribution of each independent variable in explaining the variability in the response, but also look at the importance, the biological importance of the different independent variables. Before you say, no, I can only have diameter in my model since it is explaining a lot of variability in volume, you have to look at the importance. Is it important to have height in the model? Economically, if we have height in the model, we will take more days collecting data compared to when we are just measuring diameter. So those are the things you look at, and you, given your field of specialty, you will know whether you should leave height in the model or not. So in the chat, any question? If constant, I have not seen that question. Okay. In this analysis, we are interested in the slope because our hypothesis says that there is no linear relationship between the response and independent variable. Okay, Q&A. I'm not clear about the 95% confidence level. Okay. For most of the studies we do in environment, agriculture, we normally use the 5% significance level. Now, the 5%, I mean, we normally use 95% significance level, and we use a 5% significance level. Remember that when you choose to use a big significance level, that is the amount of error you're making in your conclusion. If you're concluding that there is a significant linear relationship between volume and diameter and height, on the other hand, 5% is saying that actually there is no linear relationship. So the smaller the significance level, the smaller the error you're making in your conclusion. That is the 5% we are using in our testing of hypothesis. Okay. Okay. Let me see again in the chat. No, we do not actually use the constant. Constant is the intercept. We don't use the intercept to account for any variability or any parameter in the model. So the constant is the intercept, and it is showing us the value of the response when the independent variables are equal to 0. Okay. Okay. The question is, which one is better? R said that I've just said that it is not influenced by the number of parameters you add in the model. So initially we looked at a model where our independent response is a function of the intercept and the slope and one independent variable. In that case, our R squared can be used to interpret how good the model is, and also R squared adjust, because we only have 2 parameters. However, when we have multiple regression, we are going to add another variable here. So we add variable 2, so we'll have here x2. Okay. Now, as the more the number of parameters in the model, R squared here is influenced by increasing the number of parameters in the model. So R squared just increases, keeps on going high as you put in more variables in the model. Meanwhile, R squared adjusts for any parameter you add in the model. So giving you the correct amount of variability explained in the response. So if we are dealing with multiple regression, let us quote R squared adjust. If we are doing simple linear regression, you can quote any of the two. Okay. Organizers, why are some of us getting emails indicating that we are sorry that you are not able to attend our webinar? Okay, that is a question for forum. And we are sorry that some of you cannot get into the training because it has a cap, but you can go online, you can go on YouTube and attend the training. Okay, so let me check the chat in case there's a burning question. Okay, so let's go to something else. Before we go there, I would like to clean this whiteboard here. Okay. So there's an example here. In your free time, you can actually use R and analyze this data. We are going to use the same data set for both simple and multiple regression, but in your free time, you can raise. One thing that I want to talk about before we go to R is indicator variables. Sometimes you collect data and the data is not quantitative, it is qualitative. For example, you have things like species, variety, you have things like type of food, taste. So those variables are not continuous, they are not quantitative. So in that case, if we want to include those variables in the regression model, we use what we call indicator variables or dummy variables. Now, what we do, we give codes to the categories under that variable. For example, if the variable is type of food, so we are going to have type of food, and in case our variable is type of food, we can say maybe sweet potatoes, and then we can have cassava and maize or corn. Okay, so if we have these three categories under type of food and we would like to regress it onto somebody's income, for example, we are going to give codes for ease of analysis. We give these codes. We can say if type of food is sweet potato, we give it 0. They do not have a meaning. And if type of food is cassava, let it be 1. And if type of food is maize, maybe we call it 2. Okay. So this is how you give codes to the different categorical variables and enter them in Utah. Now this variable, you've created the new variable with this 0, 1, 2 is called an indicator variable or a dummy variable, meaning they are just for you to ease the analysis you're going to conduct. Okay. So then we regress that dummy variable onto our data set, onto our response. Now, when do we use indicator variables? When we have qualitative variables that also act as explicit. And when do you know that you need to use construct a scatter diagram? I'm just going to construct here a scatter diagram. And you find that the data is in groups. For example, you have here and then another one here. Okay. So we cannot actually fit a line here like this. It doesn't really look a good line, one regression line. So this type of scatter diagram is telling you that in your data, you have two groups. So you have the first group here and the second group, and fitting one line across the two groups does not explain all the variability in the response. So in that case, what you're going to do is to give group 1 a code and also group 2 a code, and then run a regression. If you find that the indicator variable you've included is significant, that's having one model or one regression line. So that's about the indicator variables. We are going to have a data set that shows you how to do the indicator variables. Okay. Okay. Any question before I move somewhere else? Kindly share the material for yesterday. Okay. In the chat. Okay. Pardon? Okay, the material is going to be shared. Okay. Then how many indicator variables do we need for a particular variable? Okay. The number of indicator variables or dummy variables depend on the levels under your qualitative variable. If you have two levels, then you will need only one dummy variable, because it's the number of levels minus 1 gives you the number of indicator variables to be included in your analysis. So if you have two levels or two categories, it's going to be 3. 2 minus 1 gives you one independent indicator variable. If it is 3 categories or 3 levels, then it's going to be 3 minus 1, meaning you're going to have 2 indicator variables. So let's have an example here. Okay, we are going to have an example. I hope this is visible, what I'm writing. Is it visible? Okay, so we are going to have variety here, and I'm calling it V, and I'm assuming we have variety X, and another one is Z. So if we have two levels, our dummy variable, we are going to say if variety X, if variety is equal to X, then the dummy variable will be 0. If variety is Z, then dummy variable is going to be 1. So now we only need one dummy variable. Now, how about if the varieties were 3? So we have W. So that means we need 2 dummy variables. This is dummy variable number 1. Dummy variable number 1 says if variety is X, then the code should be 0. If variety is Z, then the code should be 1, or else if variety is W, the code is also 0. So the first dummy variable is representing Z. Then the second one, 2, we are going to say if variety is X, still we'll give it 0. And if it is Z, we give it 0. And if it's W, we give it 1. Okay? So that's how we are going to create our dummy variables. And then we are going to include, so we'll have yield here, and we are going to run a regression of yield versus the dummy variable. Maybe also have site as another factor, and also put that in your model. So that's how we run we recreate the new variables and then include them in the regression to account for the groups that you've observed in the scatter diagram. Okay, let me look at the Q&A. Okay. Yeah, I've answered all these questions. Okay, and then the chat. Instrumental. Indicator variable is the same as the dummy variable, not instrumental. Okay, Okay, let's go to something else and then run to R. So I want to erase this so that we have a clean whiteboard. Okay. Lastly, when we have indicator variables, just as I'd said, we can fit a single line, ignoring the grouping, and we can only ignore the grouping if when you include your dummy variable in the model, it ends up to be non-significant. Then you don't need actually to have separate, lines for the different varieties. Now, if you find that, because here we are saying, let me go back and we are saying for single line, we have this is our data, but we are saying that we can fit one line and the line is okay. Now for parallel lines, if we include the dummy variable in our data, so we have these ones and also this one here. So what happens that if you include the dummy variable and it ends up to be significant, it is going to help you specify the intercept. So you will find that you have different intercept, and that is what we call the parallel line. So the dummy variable that you've included with the codes 0 and 1 will help you specify the intercept for the different lines. So if it ends up to be significant, then we are going to have this graph where we have two parallel lines. And in these parallel lines, we know that our slope is going to be the same because they are parallel lines. However, after putting in the dummy variable, we call the codes 0 and 1, it is significant, but we still need to explain more variability, or still the parallel line doesn't suit, we go for what we call separate lines. So we might end up having things like this. So separate lines will have separate different intercepts and different slopes. I'm not very good at drawing, but we are going to have different intercepts and different slopes, okay, in the separate line. How do we get the different slopes? What we are going to do, once you have your dummy variable, now let me clean this and show you what happens when you want to include the different slopes. Okay, so we've said that when we find that we have so if we find that the dummy variable was significant, but still we have some variability to explain, or fitting one model does not really suit our data. So this is our data here, and then another one is here. So you have a line going like that and another one going like that, meaning they have different slopes and intercepts. The slopes are different and intercepts are different. So how do we create the different slopes and different intercepts? For the different slopes, for the different intercepts, the dummy variable you created is good enough. For the slope, we are going to have one of the independent variables interacting with the dummy variable, and that is going to help us get the different slopes. So we'll have an interaction between the dummy variable and one of the independent variable, and that is going to help us get the different slopes. So probably when we go to R, we can see that and even write the models better. Okay. Okay, so I'm going to erase this and okay, so yesterday we talked about the polynomial regression, and people were saying what are powers. So a polynomial regression has a model like this: the response plus the intercept. We have the first part is the linear term, and then we have the quadratic term depending on which one. So this is the quadratic term. Okay, We could have the linear part, the quadratic part, and the cubic. Okay, so that is a polynomial regression. And in this case, we will get a graph that has a curvature. So we can get something like this. And if you fit a linear model, it will not fit so well. You can see that the linear model leaves almost all the data out. So we need to fit either a quadratic or a cubic to that type of data. So we will see that when we are in R. Okay. In the chat, let me see if you have a question, and then let's go to R. Pardon? Okay. So there are some transformations. I will not go through this. We can read, and then let's go to R. The other thing maybe to mention in passing is that sometimes the relationship is not linear, it's not curvilinear, but it's nonlinear. As I told you yesterday, when the parameters do not have a linear function with a response, that type of relationship is nonlinear. And we do not use the ordinary least square in this case, but we will go for the maximum likelihood is what we use in nonlinear regression model. So that can be a big topic for next time. And I request us to go to R so that we have a feel of simple linear, multiple, testing the assumptions, and also we look at quadratic and dummy variables. Then if time allows, we'll do model building. Okay, I'm being told that the materials of regression are in week 2, day 3. Pardon? In the Google Drive. So you go to the Google Drive and download materials for today. They are in day 3 in week 2. Okay, ladies and gentlemen, I'm going to stop sharing and let's go to R, and we open in R. We are going to open a script called Co and Regression. The script is called Co and Regression. Okay. Okay. Let me share this in the chat. Let me see in the chat. Okay. Please, the Google link has already been posted. Dr. Helen, please share again. We are turning to R, and I was told by Dr. Thomas that you are now R gurus, and I'm going to move very fast today. Okay, so somebody is asking, what's the difference between confidence interval and significance level? I have said significance level is a p-value. In this case, we are using a 5% significance level, which is equivalent to 0.05. That is the probability that the null hypothesis is assumed to be correct. Confidence interval, it involves a range of values, the lower limit and the upper limit. It consists of a range of values for the possible, either population mean or population standard deviation, etc. So confidence interval gives us a range of values for either a population mean or any parameter that you're computing. And statistically, we interpret that if you collect data 100 times. You go back to the population, collect data 100 times, and calculate their confidence intervals. 95% of the time, you're going to find them including the value of the population mean. So when you go back, collect data 100 times, compute their confidence intervals at 5%. 95% of those confidence intervals are going to include the value of the population mean, if the interest is the population mean. So that's the difference. Or sometimes we say we are 95% confident that the population mean lies within the upper and the lower limits of that confidence interval, not between, because depending on the value of the mean. So okay, ladies and gentlemen, I believe that you are all at this stage. You have this, it is called co-plot and regression. That is there. And I have several libraries I've included here. We have Tidyverse, LearnerR, Dplyr, ReadExcel, Reader. Yeah. So let's set our directorate. We got session window, set working directorate, choose working directorate, and mine is here. It's called reg, and I do open. So if I've moved so fast, it is session window, directorate, choose working directorate, browse to the directorate where you put your day 3 material, and then set that as you set it as your folder where the data is. Are we together? So in the chat, has everybody set their working directorate? Has everybody set their working directorate? Please do that. I can see no. Okay, I'm giving you 1 minute. Please set your working directorate. And if you do not know how to set your working directorate, they say I've not provided the link. Helen, please post the link again. There it goes. The link has come. So please, please download the material and let us continue. Don't work in the Google Drive. Save it on your computer. If you work on Google, you'll be left behind. Name of the file is co and regression. Let me type it in the, it is co and week 2, day 3 material. This is the file name. There you go, the file name is there. For the script, the R script, it is an R script. We can't see. Oh, okay, let me do it again. Okay, sorry about that. I thought I was posting to everybody. Okay. There we go. That is the file name. Connection is poor. Is that for me or general? Okay, that's not my question. Okay, 1 minute, 1 minute. Let us get the data set. Resend the link. Please resend the link. And in Q&A, let me see Q&A. Where can I find the files? Please send a link to Q&A. The link will be sent in a... Okay. You've sent it. In the Q&A. Just copy and answer one of them. Okay, so I believe that everybody is ready. Can we now start? Make sure you set your working directory to the folder where the data set we are going to use is. The data set is egg production. Okay, the other thing we are going to do is we are going to load these libraries. So load the first part. And if you go below here, unless if you don't have it, you see we have library car, we will need it. Library psych, we will need it. Also be needed. If they already installed, just run the second bit. And run, and we'll be good to go. So in the chat, have you all loaded the packages? In the chat, has everybody loaded the package? That language, the R language, you know, it's not English. Somebody is saying no. If you say no, give a reason. Error in library GGB. If you get an error, and if it doesn't work, leave it for now. In case we need it, we'll load it later or install it later. Error with library GGPBR. It is still loading, okay. 1 more minute for everybody. Please install those packages, install them. The link, don't get tired, just send the link. Okay, the link has been shared, please. There's one for YouTube and also for the Google Drive. So those on the YouTube, you're able also to access. So I think everybody now is comfortable. If yes, can I see in the chat whether you're comfortable? And we go on. Registration, you can register even during the break, please. Let us now save time for this because I want you to get some knowledge on survey. Okay, so some people have gotten knowledge on experimental design. Now we need you to get survey. Then you haven't installed Gmodels, please install it. Just install, write install.packages in inverted commas Gmodels. Okay. Okay, let me continue now. We are going to continue. Has everybody set their working directorate before we go on to the analysis? If you find that there is a message saying no package, install it. Somebody is saying that they cannot see. Okay, people have set their working directorate, great. Okay, let's go on. So then on line 49, and if it's not 49, then it should read eggp assign read.csv in inverted comma eggp.csv. So when you look under your console, you see water uptake, food uptake, and egg production. So this data is about rearing chicken, and you want to see how much food you should be buying, how much water for you to have maximum egg production. Okay. Okay. So is line 49 and 50 okay in the chart? Has everybody run line 49? Internet is very weak. Okay. 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 Okay, after running line 49, you should be able to look at the data set. And we are now going to go to visualization. Now we are only going to construct a scatter plot, and we are going to construct a scatter plot of water uptake and food uptake. Okay. So I remember yesterday my colleague showed you line 49. It just divides the window that you're going to have, your window, it divides the window. Here we are telling R that our window should be one row and one column. So you'll have only one graph fitting there. So then the next part is plot. So here I've given you three options. You can use scatter, you can use ggplot, you can use plot. So let's run the first one, line 60, and see what happens. So if you run line 60, what do we observe in line 60? Let me see in the chart. What have you observed in the output, in the plot window? What do you observe? What can we say about this plot? Somebody says scatter, another one linear. Let me see linear, a linear relationship. We can see a scatter. You are right. Positive correlation, great. Positive linear, excellent. Okay. Linear relationship, positive linear relationship. Yes, we are seeing a positive linear relationship between water uptake and food uptake. Okay, so we are going to get the same output even for line 64. It's just another way of constructing a scatter diagram. So you can place your cursor and run scatter.smooth, and it puts in a line through the points. So the same applies to line 67. You can use the ggplot. So whatever appears appealing to you is what you use. So line 67 to 69 gives us that plot there with a smoothing on it, a line, and the points are there. Okay, then we want to find out, is there correlation between food uptake and water uptake? So line 72, you can run attach eggp so that R remembers that it is dealing with that data set. So run line 72, and then we are going to run the correlation between food uptake and water uptake, and it gives us a value. So we have an R value of 0.9778. So in the chart, what do we think about that value? How do we interpret that value? 0.977. If it says no file directory, I clean the console. Okay, let me clean the console, but I believe you're also getting the same thing. So let me run again. There we go. Is it visible now? And what does it mean? I can see strong positive correlation, strong positive correlation. That is excellent. We have a strong positive correlation between water uptake and food uptake. Somebody is saying 90.7% explained. No, we are now dealing with the correlation, and once we go to regression, we'll be able to know how much variability is explained in the response. Okay. Okay. So the next one is the test to find out whether our correlation value of 0.9 is different from 0. So line 74 is code.test, is going to test that correlation value. So run that, and you will see that in your console, it's going to say Pearson product moment correlation, the t-value, the p-value, the freedom and p-value. So here it is saying alternative hypothesis, true, correlation is not equal to 0. So that is alternative hypothesis, that the correlation between water uptake and food uptake is not equal to 0, or there is correlation between water uptake and food uptake. So since our p-value is so small, which is 0.000004, we conclude that there is a significant, strong, positive linear correlation between water uptake and food uptake. So with the code.test, it even gives you the correlation value. It gives you the 95% confidence limits or interval for that correlation value. Now, what if you want to get correlation for all the variables in the data set? So long as they are all continuous, we can use core in brackets the file name, and it will give us correlation for all of those. So run line 75 gives us correlation values for all the variables we have in the data set. So you can see in the output, water uptake and food uptake is 0.977. We've already seen that. Water uptake and egg production is 0.79, etc. Okay. So if you no longer want to use egg P, you can detach using line 76. So if you detach, meaning that wherever you write an R command, you're going to remind R that you're using egg P. Okay. I will clear my console again. Now we are going to run our simple linear regression, and it's going to be between water uptake being our response and food uptake being our independent variable. Okay. So the line 83 model is the object name given to that regression analysis. LM means linear model. So that is the function we are using. Water uptake is a function of food uptake, and data equals egg P. So run that, run line 83. And for us to see the output, you have to print the model. So print model, then it gives you, so when you use LM, it gives you the intercept and the slope only. For you to be able to get the ANOVA table and the R squared, all that, you have to put summary in bracket model. So when we run line 85, it gives us more than what the model gave us. So we get, if you see the results of summary model in the console, we have the formula, water uptake is a function of food uptake. We have residuals, the minimum residual, the first quarter residual, and the maximum. Then it also gives us the coefficient. So let's look at the coefficient, ladies and gentlemen. Coefficients in your console, you should have coefficients. And we are interested in the hypothesis that the null says that there is no linear relationship between water uptake and food uptake. And we are testing that hypothesis at 5%, which is the same as 0.05 probability. So when we go to the slope, it's the one testing the linear relationship, and the slope corresponds to food uptake. Our estimate of the slope is 2.733. The p-value corresponding to the slope is 4.02 to the power minus 8. Now that value is smaller than 0.05, the level at which we are testing our hypothesis. And it is also significant at 0.0 something percent, 0.001, 0.00. You can see those stars, means that it is significant at all these levels. So since it is significant, we have evidence to reject the null and conclude there is a significant linear relationship between water uptake and food uptake. We can write our regression model being that water uptake is equal to minus 63.5131 plus, because this value is positive, plus 2.733 food uptake. So for purposes of interpretation, for every unit increment in food uptake, water increases by 2.733 cubic liter, cubic millimeter, depending on the units of measurement in your. Okay, when we go down, I'll as well check the chart. Okay, when we go down, we will see multiple R squared, which is the R squared. It is 0.9562, and R squared adjust is 0.952. So that tells us that the amount of variability explained in water uptake is 95.6%. So most of the variability in water uptake has been explained by the regression model. Relationship between the t-value corresponding to food uptake and the F statistic. The F statistic here in the console is 218.6. If you have a calculator or you have your phones, can you get the square root of 218.6? What is the square root of the value of F statistic, which is 218.6? For that, okay, 14.8. Another one, thank you. Another one, what do you get? Square root of 218. Square root of 218, 14.785. Okay, yes, that is the value, 14.8, 14.785. Thank you very much. Now, let's look at food uptake under coefficients, ladies and gentlemen. Look at coefficients. When you go along food uptake, you get a t-value. And that t-value is 14.78. So that means that you've gotten the t-value. The square root of 218.6 is the t-value. And you can see that the p-values actually are similar. So the null hypothesis of no linear relationship between water uptake and food uptake can be tested by either the t-test or the f-test. And the relationship between the f-test and t-test is that if you square the t-value, you get the f-value. If you get the square root of the f-value, you get the t-value. Okay? So when you're doing your analysis, you can always cross-check whether your results are correct by doing those simple math. Okay. Okay, let's go ahead. I hope it's all okay. Now, we can actually produce the R squared using summary model R dot squared. Lines 86 gives you the value of R squared, which we've been already talking about, and you can also get the R squared adjust. So this is just extra code for you to use. In case you want to get your R squared or you're doing model building, you can always use summary model $ adjust. So you're telling to summarize the model, but you only want to print the R squared adjust, or you want to print R squared. Then also there are other criteria you can print. For example, AIC is a Kakai information criteria, and BIC is Bayesian information criteria. So those two are used to assess the goodness or fit of the model. If the model fits well your data, then we should have small AIC. We can only interpret those values if you're comparing more than two models. So if you have model 1 and model 2, you are choosing between those models, look at the value of AIC. Whichever model has a small AIC or small BIC, then that model is good. So what does AIC do? So when you have a model with intercept, both AIC and BIC, it's comparing the information lost when you add in another variable into the model. And if that information lost is small, then the resultant model is good. That is in layman's language. Okay, let me see in the chat. Okay. If the p-value, where was that? In the chat. If the p-value is greater than 0.05, then we have no evidence to reject the null hypothesis. Conclude, there is no significant linear relationship between water uptake and food uptake. So we end there, the model ends there. We can't use it for prediction. We don't even need to go and assess the assumptions under that model because the relationship is non-significant. Okay, let's go on. AIC is Kakai information criteria. BIC is Bayesian. There is also what they call Bayesian statistics. So Bayesian information criteria. The two criteria are used for testing how good the model is compared to it. And a model with one variable. You want to find out whether you should go with a model with the intercept alone. You produce the AIC for the model with intercept alone and also with a model with one variable. So whichever of the two models has a smaller AIC is what you choose as the best model for your data, or a smaller BIC is what you choose for fitting to your data. So those two, we shall see them in model building. They are mostly used when you have so many variables in your data set and you want to fit all of them onto the response, but then you don't know which variable to drop, which variable to leave in the model. So as you remove one variable, you check the value of AIC. If it increases, then that means that resultant model is not good. So for every model, the AIC should be small for the model to be good for prediction. Now, we can also use the command AOV. You get results also using the command AOV. So I'm clearing my console. Model 92 line 92 uses AOV to do regression instead of linear model. So if we run that and then run our summary, we will see that we have the coefficients given and also the corresponding significance codes. Okay, but this is just, by the way, you can use LM, you can use AOV. Okay, so if we want to add a regression line to our scatter diagram. Then we use ggplot. So if we run line 109, it gives us a regression line added on to our model. So we are going straight on to testing the assumptions under simple linear regression. Between the response and the independent variable. The second one is that the residuals should be normally distributed with mean 0 and constant variance. They should be independent. And also the response should be normally distributed with mean mu and constant and variance sigma squared. Okay, so if you want to do, we run the model again. And this time I'm using LM. I found it's more friendly than ELF. So I'm rerunning my model too using LM. In your script, you LM line 140, it's model 2, assign LM instead of off. So we are good to go. So in the chat, have you understood what I'm talking about? No. Okay. Not clear, no. Okay, when you go to line 140, if it's not line 140, go under checking assumptions. You will see a code, a command model to assign, instead of A of V, change it to linear model, LM. Only that. Change to LM. And then let's so if that is done, let's run line 140 or the line that is in your script, and also the model summary, which we've already had. Now, the second part, we are instructing R to divide the graphical panel in a 2x2, 2 columns and 2 rows. So please run 143. Is everybody at the same pace with me? We are the same pace, 143. Ladies and gentlemen, are we okay? Can we go ahead? Because to be left behind. Okay, somebody says I should go slow. Okay, great. I will. I'm switching on my speed governor. Okay. Some people are saying no. If you say no, please put a reason why you're saying no, so that we know the problem. Okay, so I've said run line 143, and it divides a plot section into 2 columns and 2 rows to allow us fit in our plots. Okay, and I'm just using the clearing a yellow broom to clear my plot section. So there is a yellow broom there. If you click it, you clear your plot section. So then let us run plot in bracket model 2, and that gives us residual plots for testing our assumptions. So let's run that. Oh. Okay. It says I should hit enter. There we go. So when you run plot model 2, in the console, you will see return to see the next plot. So you hit enter to see the first plot. So the first plot we are seeing is residual residuals versus fitted value. And this plot I said yesterday is used to test the assumption of constant variance of the residuals or to test homogeneity of residuals. So here we see that the dotted line you see in black is denoting that the average value of residuals is 0, the mean of residuals is 0, and we should have at least the points randomly scattered around that line and no pattern. So you can see that except for these ones which have been labeled 11 and 7 and 6, so we have 11, 7 and 6 are showing that you might have some values which are outliers. So we will see as we go ahead whether that is true. So that, because we are seeing a random scatter of points, we conclude that the assumption of constant variance is valid. There's no pattern that you're seeing. So in the console, they say it return the next plot. The next plot is a QQ residual plot. Has everybody gotten the QQ residual plot? Okay, let me check in the chat. Please repeat. Okay, I don't know. I don't know what to repeat, but let me explain this QQ plot, then we'll see about the first plot. The QQ plot is for normality. You see a dotted line. If they follow the residuals, follow a normal distribution. And still in the graph, you can see that 0.6, 7, and 11 have been highlighted, meaning that they are possible outliers. We shall see about that. So once points fall on the dotted line, then our data is normally distributed. The next plot. The next plot is a scale location plot. And it is the square root of standardized residuals versus fitted values. And it also tells us that our data, it talks about constant variance. It is testing for constant variance and also highlighting some observations as outliers. Okay, then if you hit enter again, you'll see the last graph, residuals versus leverage. Now, this one is the one going to tell us whether we have influential observations or outliers. So the dotted lines you see on top here, we see let me zoom out and then stop sharing and share this. I am going to share this graph alone. So there we are. So I hope this is visible. Residuals versus leverage. Now, we see these dotted lines, the black dotted lines at the bottom and also at the top. Now, in case any value lies above these dotted lines, then that value is denoted an outlier. So we see that all these values actually they've indicated are all below the dot. Value greater than the Cook's distance. you can see here it is called Cook's distance, not the other one who cooks food, but here in statistics, any observation that is above the Cook's distance, here at the bottom and also on the top, it is denoted an outlier. And in this case, we do not have any value below here or above the dotted lines. Is that clear in the chart? Let me see in the chart. Okay, Prof, the network is not stable. You might be right. Oh, the figure take long to come. Okay, I'm going to repeat this one. I'm told the network is unstable and the figures take long to come. So I'm saying that the dotted line, they indicate the Cook's distance, these ones here. Anything above these lines is denoted an outlier, and anything below these lines is also denoted an outlier. So if we see an observation highlighted by R and it is falling here or falling above here, then it is an outlier. Okay. Okay. So I will stop sharing this and share and then share the R script. Okay. Now we can actually produce these plots in one go. So I told you that when we run line 143, since I didn't run it, so let me run it and then run plot. And you can see that all of them are produced at a go, and you can export them. You use the export button to export them as images, or you can paste them on the clipboard and be able to insert them in your document. So the 4 graphs can be produced at a go. Make sure that you run line 143 and then you run the plot model. Okay, I am going to the next one. Spheral test, it is used to test the 6. Let me clean my console and run again. Line 146 is testing for residuals, whether they are normally distributed or not. The null hypothesis here is that the residuals are normally distributed. They follow a normal distribution. And alternative is that residuals do not follow a normal distribution. When we look at our p-value here, I hope you can see the p-value in your output in the console. It is 0.6077. This is greater than 0.05, meaning we have no evidence to reject the null and conclude the residuals follow a normal distribution. Okay. In the chart, is that okay? Can I see in the chart whether the interpretation is fine? And we continue. Okay, that is great. Great. And in Q&A, let me check also Q&A and see what threshold of AI. Okay, I'll answer that later. Okay. Then the next, line 149 is test for independence of errors. We want to find out whether the errors are not correlated. So we use that down Winston test. And if you run line 149, let me also clear the console again and run because I want you to see. So here, the null hypothesis is that the data is correlated. The null says the data is correlated. The alternative is that rho, which means the correlation is equal to 0. Meaning the errors are not correlated. So if we look at our p-value, Is it true? Oh, the null hypothesis is that the data is not correlated versus the alternative is that the data is correlated. Now our p-value is 0.4, which is greater than 0.05. And we conclude that our data, the errors are not correlated. Then we also have a test for linearity, line 151, the CR plot, it tests for linearity. And if we run that, we will see a plot of water uptake versus food uptake. And if the points follow on the pink line, there is a pink line and a blue line. And we see that the pink line and the blue line are overlapping. In case one deviates from the other, then we have, then the two variables are not linear related. But here we see that both the blue line and the pink line are fusing into each other. They are overlapping, meaning that the two variables are linearly related. Lastly, but not least, we also test for homogeneity or variance among the residuals. And we use the NCV test. Make sure you run the library car. If it's not loaded, please load it. I've already finished loading library car. And if you didn't load it, you load it before you can run this test. And when you run the NC test, it's non-constant variance test. It will tell us whether what we saw in the plot is what is in the result. So again, let me rerun this. And our null hypothesis is that the variance is constant, and the alternative is that the variance is not constant. And because now the p-value is bigger than 0.05, we conclude that the variance is constant. So this data and the model we've applied, the data suits the model, and also the assumptions under the model have not been violated. In the chart, let me see in the chart. Any problem? Line error in line 149. Yes. Let me see, 149. I have error. What is intercept? Okay, no problem. Okay, the errors are moving so fast, I can't even read them. Okay. Okay, so let's have one person. Okay, Musinguzi, can you, David of Reform, can you promote Musinguzi? Is that the right name I saw?
Prof,
let me go back.
There are two Musinguzis. I'm seeing Noah and Levian. Which Musinguzi?
Okay,
Let me Musinguzi Noah and then Musinguzi Levian. Maybe
okay.
they can, the one you are referring to can raise his hand.
The Musinguzi was a problem, please. Can you now say yes, it is me, so that you can be allowed to share your R script? I'm told
he can also raise his hand. He can raise his hand and then I can.
Please raise your hand also. Musinguzi, you had an error. Prof, would you repeat the scale location? Okay. Let me check through this. Oh dear.
So
Simon Peter, just zoom in your RStudio, go to view and zoom in. That problem will be solved, or figure margins will be solved. That is not a big problem, but somebody here had an error in line 49, and I'm looking for them. Okay, somebody had an error on line 149. Can you please put up your hand if it's true you had an error, because I can no longer see you in the chat, so that you can be promoted. I can say, okay, let's see, new error. Okay, let's have, what is her name? Samehe. David, can you promote Samehe?
Same.
Yeah, Sameh. It is S-A-M-E-H. That is the name.
Same.
Yeah.
Yes, Same. Okay. We are promoting Same. Same, you should
Okay.
be.
Somebody has an error, could not find a Durbin-Winston test. That means you did not load some packages. That is the problem you have. There's an error in line 156. Yes. If you have William, make sure that you corrected the line I talked about. Instead of using AOV, put LM.
Prof. Same has declined to be promoted, so maybe you might have to select another person.
There's also error in line 156. Moses Asinde. Moses, can you put up your hand so that you can be promoted, and then we can see that error in line 156. Where to put LM, and LM should not be capital. Okay, if you have a problem with line 156, put up your hand and you're promoted. It will sort the problem out, okay? If you have a problem with line 156, put up your hand so that you can be promoted. So David, whoever you see putting up the hand, let them be promoted, because I can see the same problem coming.
Promoted in Mary.
Okay.
Mary.
Okay, we are going to solve that of where to put LM.
Mary, please go ahead and share.
Okay, Wilfred, that is great.
Unmute yourself, Mary.
Good evening, Prof. Can you hear me?
Let me stop sharing. Sorry about that. I had blocked you. I couldn't see you. Okay, Mary, go ahead. I can see your name, but not the script.
Just a minute. Let me share my screen.
Okay. Okay, okay. Yes, go. Can you scroll up? First scroll up. Up to line 140. Okay, there you go, line 140. For everybody, please pay attention. Scroll to line 140. It says model 2, assign instead of AOV, put LM. So change it to LM. Okay. Then let me wait for everybody. Has everybody corrected that mistake? It was a mistake that I put AOV, and Tapias doesn't go well with that function of. So if you have corrected line 140, then run line 140. Okay, so first clean your console using the broom. Clean. Yes. Great. Okay, run line 1. Yeah. And then run the summary. Okay, great. So I believe that everybody has gotten an output which resembles Mary's output for line 140 and line 141. Is that okay? Should we go ahead? in the chat? Are you seeing yes, yes?
Prof, I also promoted is it Celso? I was Celso Mondlane.
Celso Mondlane.
Yes.
Okay, when Mary is done, we will see yours, okay? Wait a minute. Okay,
No.
Mary,
I think
Yes.
that is a screen.
Now
a
it's
screen
Celso,
from
the one
Celso.
who has been promoted.
oh, the other one has gone.
Hello.
Mary is still also around.
Okay, Mary, go ahead. Now go and run line
But this is
150.
Celso. This is
Okay.
Celso who is sharing the screen.
Okay, first wait, Celso, before you share the screen. You wait for Mary to finish. Mary, can you go and, oh dear.
I got
That was-
156.
Yes, and run line 156 that had refused to run. But you have to share the screen. Has it run?
Yeah, it has run. I share my screen, you see?
No, it is okay. Let's Celso share. Since the problem is sorted, let's see Celso's Celso. Oh my goodness, your name. I can't pronounce so well. Okay, thank you, Mary. Let's see the next one. Okay, you can mute yourself, Mary. Thank you. Okay, now what is the problem? Go to line 140.
No, it's
Scroll.
already okay.
It's already okay. Have you run it?
Yes,
Again?
I ran it because I was the one who was sharing it.
Ah,
Was not Mary,
Okay, then-
I was the one.
okay, then
it's
run
okay.
line 156.
Yes,
Run
it's
line
already
1.
run.
It's already run.
Yes.
First,
Yes.
clean your console so that others can see. And then run it. Okay, so whoever corrects line 140 will be able to run line 156. Just replace the AOV with LM and run, and then you come and run line 156. All be sorted. Okay.
Okay.
And there are some
Thanks.
people who had a problem with the Dubbin Whiston test. That means there is a package you've not installed. Please go and install those packages. That is the problem. Okay. Go and install those packages. And I can see here, Baku, the problem be sorted by installing the packages. So install all of them and then load them. Okay. It's solved. Okay. Great. The packages. Okay. To fix that error, please install package car. Okay. So you've been told to fix the problem. Let me share mine. So when you install package car and load it, you're able to run all these other ones. The Dubbin Whiston test, the CRP plots, etc. If you don't load and install that package, you'll not be able to run those tests. Okay. If that is okay, can I see in the chat in case anybody has a problem in the chat? I have package problems. What is the problem, my dear? Can you indicate the problem in the Q&A? My colleague will help you. Has the problem been sorted? Is it okay? No problem. Let me see in the chat, say no problem or okay. Then I'll know that you're fine and we go to another bit. Okay, great. If you have problem with the package, please put your question in the Q&A. My colleague will help you with the package that is not installing. So copy and paste your error in Q&A. Thank you. Okay, let's go ahead. Okay, we are going to check for outliers and influential observations. So we use the outlier test still for that same model. So line 160 helps us to test for outliers. And let me first screen my console and rerun it. Line 160. and you'll see that in case any value, you see number 6 was highlighted in the graph as being a possible outlier. It has a residual of -3. And now their testing is to see whether it's an outlier. And here the p-value obtained is greater than 0.05, indicating it's not an outlier. So for you to know whether it's true, it's not an outlier, we've created an object out1 as dot numeric, names, all that, Bonifera, the same test. And then it's going to tell us that we don't have any outliers. So out1, it would have highlighted the outliers in the data set, but we see we have 0 outliers. Then to indicate the influential values, we use line 163. And if you run it, it gives you the diagnostic plots. And you can see that it has the Bonifera p-value here and the index. So all the observations here are indicated. And you see that number 6 here appears like it's an outlier, but it's not. We've already tested. And is it an influential observation? It appears like, but we can also use the Cook's distance to test whether observation 6 and 11 influence our parameters. So the next part, which is Cook's distance, is going to help us to see whether any of those values is actually influencing the value of the parameters. So line 165 is the Cook's distance. We are going to calculate Cook's distance for all the observations. And we are calling that file CD. Then we are saying influential is equal to which? In case any of these values in CD are greater than 1, then they will be printed out in this object of line 166. So if we run that, let me clear my console and run it again. If we run line 166 and run, it says no influential observation. It says name the integer 0. So it is just showing us that all those observations actually are not outliers. They are not influential observations. Okay. And line 168, still, we are constructing a plot. If you run, you will see a plot which is showing us these values which were one time called influential, but they are not influential because they are within the Cook's distance value. So there is a formula for calculating the Cook's distance threshold. It is Cook's distance is equal to 4/n, n being the number of observations in the data set. So you can calculate that value. It is Cook's distance is equal to 4/n. You don't ask me where the 4 came from. I also saw it in literature and I haven't researched it so well. So here you can see they've indicated Cook's distance on the plot from 0 to 0.2. So the threshold is 4/n, and we have 12 observations. So 4/12 should be your threshold, which you use to determine if an observation has a Cook's distance greater than 4/n, then that is influential. It is going to affect our values of the slope and intercept. Okay. Any question in the chat before I go to multiple regression? In case there is influential, what do? We can do two things. We can remove the influential observation and then analyze our data, look at the values of the parameter, the intercept and slope, compare with the model with the influential observations. If the change is not big, then we leave it in the model. If the change is significant, we can test the two values of the intercept and slope. We can use a t-test and see whether the difference is significant. If it's significant, then that influential observation, if left in the model, it's going to affect our slope and intercept. So it has to be removed. Please remove Cook's I said the Cook's distance has a threshold. Let me write here, Cook's distance has a threshold which is equal to 4 over n, small n, where n, oh, I'm writing here, let me post it. I've written it in the chat. Cook's distance has a threshold of 4 over n. Any value in the observation with a Cook's distance greater than 4 over n, it is labeled an influential observation. Okay. So you can see value 6 and 11. They are not influential. If you get 4 over 12, what do we get? If we get 4 over 12, it is 0.33. So look on the graph. Are their values greater than 3.3? No. So 6 and 11 are not influential observations. Okay. Thank you very much. I've seen people who have calculated. How is 4 derived? That's what I told you, that I read it in literature and I need to find out how 4 is derived, but I just saw it in literature. So I also decided to share. So you can go in literature and find out how was 4 derived. Okay, break time. You are right. We need break time. Even me, I need break time. So let's have 8 minutes of break time. So we come back at 4 Ugandan time. So at 4, oh, some people are saying that I should give them their full break time. Okay, come back at 2 minutes past 4. Okay. How was 4 derived, please? Nora, I've said that it is in literature. I'll refer to that literature and we can read it together with you and find out how 4 was derived. We need to do some math. Okay, thank you very much. You've been very good participants. Go for a break. 4:02, let's come back and finish. Okay, great. David, can you allow me share? Thank you. Ulanze nokusmiling, asmile nichiza. Smiling all the time. Okay, ladies and gentlemen, welcome back from the break. I hope you had a cup of tea. Me, I was here waiting for somebody to offer a cup of tea. Nobody offered, but I'm fine. Let's continue. Okay, now we are going to look at multiple regression. We are going to look at multiple regression. Okay, I remember multiple regression involves regressing one response on more than one independent variable. So in our data set, we have three variables. We have water uptake, we have egg production, and food uptake. So the first thing we do for any of these regression, the descriptive statistics we do is to construct a scatter plot and look at the type of relationship we are dealing with. So we are going to construct a scatter plot for all those three. So let's run line 173 and then 170. Yeah, line 172 and 73. So when we run it in your plot section, you will see that we have water uptake versus the second column is food uptake. The third column is egg production. So you see water uptake is positively linearly related to food uptake, but it applies also to egg production. You can see water uptake is positively linearly related to egg production. And egg production and food uptake, this is the sixth graph on the second row, the third graph on the second row. It is food uptake and egg production. You can see this relationship here. Let's see in the chart. Should we say it's linear, or what type of relationship do you observe between food uptake and egg production? Let's see in the chart. Okay, people are saying linear, 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 linear. Okay, great. It is linear. Okay, positive linear. Thank you very much. It is positive linear. So in your project, in case you're going to use regression, the first thing you do is construct a scatter diagram, which tells you what type of relationship you're dealing with. And you can also know the correlation magnitude. For example, here, water uptake and egg and food uptake has a strong correlation, which is up above 90. But when we go to egg production and water uptake, it is moderate. You can see, should be around 60 or 70. That is the rough idea of the magnitude. So you can talk around, you can copy, export it to your clipboard or save it. If you click that export button, it allows you to save as an image, save as PDF, or save as clipboard. And then you can clip it and put it in your document and write around it. Remember, when we are presenting graphs, figures, a graph, we put the title below the figure. Next, let's run our regression. Model 3 is the object name, and LM is our function. So water uptake is a function of food uptake and egg production. And our data is still egg P, so you don't need to set the directorate. So when we run that and we run summary of the model, we are going to see in the console, that we have residuals, then we have coefficients. We are testing the hypothesis that the no linear relationship between water uptake, food uptake, and egg production versus the alternative that there is a linear relationship. We are testing that hypothesis at 5%. And when we look at the p-value corresponding to food uptake, it is 1.04 times 10 to the power minus 5. It is small compared to 0.5, indicating that we reject the null and conclude that there is a significant linear relationship between water uptake and food uptake. When we got to egg production, the p-value is 0.33335. It is greater than 0.05, meaning there's no relationship, there's no significant linear relationship between water uptake and egg production. So we can now get literature to support our results. Is it true that the relationship between water uptake and egg production is not linear? So we read literature and support our results. But the statistics here shows that there is no significant relationship between water uptake and egg production. R-squared adjust. I told you when we are doing multiple regression, let's look at R-squared adjust because it is adjusting for all these parameters added in the model. So it shows that 95.2% has been explained by the regression model. The variability in water uptake, 95.2% has been explained by the regression model. Okay. It also gives us an F value on 2 and 9 degrees of freedom and a P value. So overall, it shows us that there is a significant linear relationship between water uptake, food. However, when we look at individual variables, only food uptake is contributing to this result being significant. Okay. So then we can run the same test for assumptions that we had before in the linear regression. When it comes to correlation, we can also run the correlation tests and find out whether the independent variables are correlated. That one, I'm leaving it to you. Since we are running out of time, please go and find out whether the variables are correlated. Now, let's go back and look at the script. The next thing, we can produce confidence interval for all the independent variables that we have. And you can see if you look at egg production, the confidence interval ranges from -10 to +3. So you remember I said confidence interval is a range of possible values for the given parameter. So for the slope of egg production, one of its possible value is 0, confirming what we saw in the result up here, that there is a non-significant relationship, linear relationship between water uptake and egg production. I'm going to repeat. I'm saying that when you look at the confidence interval corresponding to egg production, the slope of egg production, it ranges from -10.466 to +3. So if you list all the possible values between -10 and 3, one of the values is 0, meaning that the slope for egg production is equal to 0. And when the slope is equal to 0, it means that there is no linear relationship between production. So this confidence interval is also confirming the result you've obtained in the regression analysis. In the chart, is that okay? Should I continue? Should I continue in the chart? Okay, okay, okay. Thank you. So alternatively, if you look at line 184, if you have so many variables, instead of listing the variables, you can just say model for LM, water uptake, is a function of dot, comma, means that you have so many variables listed in egg P. So if we run this line 184, you're going to get the same result like before. So you can see we are getting the same result like before. So this is an alternative way of writing your regression model. Okay. Now, we can also find out whether our independent variables, egg P and food, egg production and food uptake, have high variance inflation factor. The VIF tests whether there is multicollinearity among your variables. Multi means many, collinearity means correlation. So are your variables, egg, food uptake, and egg production correlated? We use the VIF function to tell us whether they are correlated. Now, there are various schools of thought. One school of thought says if the VIF is greater than 1 for any of the variables, then there is high collinearity. In R, it says if VIF is greater than 5, then there is multicollinearity. And that VIF goes hand in hand with your R squared. So let's run line 191. So if we run line 191, we find that the VIF values given are 3. Let me remove this and run it again so that people can see them visibly. So we see that when we run VIF, VIF means variance inflation factor. So those values are 3.4, meaning that the correlation between these two is not so, there's no need for worry. According to R, it's not greater than 5. However, we can also test it using the square VIF and check whether we have a problem of multicollinearity. So line 193, if we run it, we see that it is saying false, false, meaning there is no multicollinearity. If it was true, true, then there would be multicollinearity. And when there is multicollinearity, we can either use weighted least square instead of ordinary least square. What is weighted least square? We get the mean of each of the independent variable create new variables from those variables. So food uptake, get the mean of food uptake, subtract from the original values of food uptake, then the resultant variable is what you use in your regression. That is weighted mean. Then you can use multivariate. Multivariate deals actually with correlation. For you to run multivariate regression, the variables must be highly correlated. So it will sort out your problem of multicollinearity. Okay. In the chat, I think this script ends here in the chat. Can we continue? Please repeat. Eric, what should I repeat? Should I continue? Everybody says yes, except Eric. Please continue. Okay, Katie, I'm going to continue. We continue. Okay, we are going to stop as far as this script is concerned. In a summary, I'm saying that the VIF tests whether your independent variables are correlated. And R, from what I read from R, it says that if VIF is greater than 5, then the two variables have a problem of multicollinearity. So please always read a statistics book that you will use to support your results. Now, down here on line 193, we've tested whether there's a problem of multicollinearity using square root in bracket VIF model 3. And when we ran that, we found out that there was no multicollinearity. It's saying false, false, meaning no multicollinearity. If it had said true, true, then the two variables would be highly correlated, and the correlation is likely to affect your results. Mult means many, collinearity means correlation. I don't see the cursor moving. This leads to confusion. No way, Olivia. I'm just talking. So, okay, here is the cursor moving. Oh, output. How is the output sent to Microsoft Word? You just copy here in the console. Hope you are seeing that. Right click or use Control Copy, Control C, and then open our Word document and paste it there. What is true? What is false? True means, from the word true, it means it is right. So if that test gives you true, means that there is collinearity. If it gives false, false, it means there is no collinearity. And remember that we've said square root of that value is greater than 2. So meaning that when you square that value, we don't get anything greater than 2. How about R Markdown, Prof? Oh, alternatively use R Markdown need to. Okay, yes, 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 you're right. Francis, thank you so much. But with R Markdown, you have to get your script, open it in R Markdown, run it. Then after you've run it, it will produce everything in R Markdown. Then you open R Markdown in your Word document. Or you can actually save R Markdown as a PDF or as another extension. What's the difference between cooking and cook's distance? And cooking data. What's the difference between what? Oh, cooking data and cook's distance. Okay, cook's distance is a test that helps you to know whether the individual observations in your data set have an influence on the parameters in the regression model. Meanwhile, cooking data is falsifying your data. When you don't present the correct data, then that is cooking data. In case of multicollinearity, I said we use either weighted least squares or weighted regression. Go and read about weighted regression, weighted least regression, squares regression, please. I appreciate RStudio, no Excel graphs. Okay, if you find that there is multicollinearity, you can either use weighted least squares regression or you use multivariate regression. So write them down and read about them in your free time when you're taking a cup of tea. Okay, let's go to the something in the last 30 minutes. We are left with. Is there anybody who is lost? Because we are going to close this script and open another script. Prof, please repeat that. I said, if you find you have a problem of correlation, I'm going to talk as a layman, of correlation between your independent variables, then you have to use weighted least squares regression or multivariate regression. That's what I said. Okay, thank you very much. So now we are going to use a script called regextra, regression extra, meaning we are going to look at curvilinear regression and or polynomial regression and also something. Okay. Okay, let's open that script. It's called regextra. The data sets are still there. So forget about, let me write in the chat. It's called regextra. So that is the name of the script we are going to use. And it has data, we are going to use a data set called uptake. This was an experiment to find out how much carbon dioxide is absorbed by plants if they are exposed to carbon dioxide. So a certain amount of carbon dioxide was passed onto the plants. And then after some time T, they measured how much content of carbon dioxide was in the leaves. So that is the data set. Okay, ladies and gentlemen, I think that everybody is fine. Since we've already loaded the packages, we don't need to load again. Let's just go and read our uptake. If you don't close R and open it straight in R, then you don't need to load the packages. But if you close R and then you go to open this script, we might need to load some packages. So I hope you just opened it. So let's read in this data set. And line 1, it's read uptake is the object name, read.csv. When you run it, you will get your data. And this data set consists of time, uptake, and iron. So under iron, we have rubidium and bromide. I know some of you are not chemists, but in my O-level, we used to do some chemistry. That's how I know the things of rubidium and bromide. O-level, they have year 11, year 10, you do the things of chemistry. Okay, so these are plants being exposed to carbon dioxide and then time taken to absorb carbon dioxide in presence of rubidium and also bromide. So We are not going to draw the scatter diagram, but I think we should. And remember that we have a categorical variable, which is rubidium. And I want to create a variable with the codes where rubidium will be 0 and bromide will be 1. So the next line is to create a new data set. So we are saying uptake, look for iron. The object name is uptake $iron1. Assign if else uptake $iron is equal to rubidium. Then give it 0, otherwise 1. So that is line 4. So I'm going to run line 4 and view my data. So when you see in the R Studio, you will see that our data set has now 4 variables with time uptake iron and a variable called iron1, where we have codes for rubidium and bromide. So we can X that out on top here of R Studio, X that out, R Studio, and then we go to line 7. Line 7 just tells you the names of the columns in your data set so that you write them correctly. So there we go. And then we want to plot our data and see really, do we need what we think, what I'm thinking? So line 8 is a plot scatter diagram. And you see that this is the data. So from this data set in the chart, what do you see? Kindly send me the link. Okay, the link will be sent. There you go. Okay, positive correlation, positive collinear. No, there is no positive collinear, my dear. It is positive correlation, positive linear correlation. Okay, this is positive. Do you think that we have 2 groups in the chart? Do you think we have 2 groups in this data set? Warning, you didn't set your directorate, my dear. Somebody who has file not found? Okay, thank you. Somebody has file not found, or set your, go to session window, set working directorate and choose the working directorate. Browse to where this data set was saved, please. And there you will set your working directorate. Okay. Okay, so we see that in the plot section that we are likely to see 2 groups, one on top, one above. If we put in a straight line here, it may not explain most of the variability. So probably we need 2 lines, one going through the top and one going through the bottom. But let's see whether that is true. So the first thing we are going to do is to run our model. We are running a model of uptake as a function of time plus iron1. Iron1 is the dummy variable representing the categorical variable iron, rubidium, and bromide. Okay. So I'm running line 9 and the summary. So let's go to the console. Ladies and gentlemen, are we together? Let's go to the console. We are testing to see whether there's a linear relationship between uptake of carbon dioxide and time taken to absorb the carbon dioxide. And we see that from our p-value, there is a significant linear relationship between uptake of carbon dioxide and time taken to absorb the carbon dioxide. And also check the iron1 is significant because its p-value is 8.02 times 10 to the power minus 6. So when that is significant, what do? We realize that we cannot fit a single model, but we require a model, two models, one explaining bromide and another one explaining rubidium. Here in the R squared adjust, our R squared is 0.9855, indicating that 98.55 variation in uptake has been explained by the model. Okay, ladies and gentlemen, this one I want to type, and we see the difference between having no iron 1 in the model. What does it do? I'm just going to type, so don't get confused. I'm pasting the same thing as above and removing iron 1. So you can see what I'm doing. I have removed iron 1 and left my model. I'm going to call the object 1. So it's model 1 or mod 1 is equal to LM uptake as a function of time only. I want to see the difference, whether should we go ahead and include iron 1 to separate the two lines which we've observed in the scatter diagram, or we just fit one line onto that data. That's what I'm doing. And I just copied and removed iron 1. So I hope that is okay with you guys. Okay, line 12, which I've just pasted in, I'm going to run it and run the summary. Oh, sorry, it gave me a different result. This is iron 1. Okay, so run line 12 again, and then run mod 1. Okay, so I want you to pay attention to the R squared. If we look at R squared, when we only have one variable in the model, the amount of variability explained is 0.7725, which is 77.2% of the variability in uptake. And a whole around 23% variability has not been explained. So that shows us the importance of adding iron in the model. When we had iron 1 in the model, the variability explained was 98.2%. So ladies and gentlemen, are we understanding what I'm doing, or I'm talking to myself? Somebody, Prof is using R software. Yes, dear, I'm using R software, so I don't know what you're saying. Are you guys understanding? Do you see the relevance of using a dummy variable? Here, I'm showing you the relevance of using dummy variable. And we've seen that in this case, we need parallel lines. We cannot, where is the cursor? We cannot use only a single line to go through our data. Okay, so repeat on dummy variable. I'm not going to repeat so much, but I'm saying that we had a categorical variable which is named iron, and created a new variable called iron 1 with codes 0 and 1 to represent rubidium and bromide. And when we included it in the model, the amount of variability explained was 98.2%. When we run a model with only time alone, we see that the amount of variability explained is 77.2. So there is an improvement in the amount of variability explained when we include iron in the model. Also, when we look at our scatter diagram, we see that there are two parallel lines here which we need to fit onto our graph. So how do we fit those parallel lines? We are going to do a bit of math. Let me just clean this and run again. So we are going to forget about this single line here, since we've already known that actually running a model with iron is important. So I'm going to run iron again with time. So this is our output. We say that for rubidium, it's coded 0. So wherever you see iron 1, substitute with 0. So the first model for our data is going to be the intercept and the value of the slope, which is 0.181. So let me use my writing pad. So the model for rubidium is going to be equal to 2.7, maybe 7 plus 0.181. That is the model for rubidium. Because where there is iron 1 here, we've substituted with 0. The second model for bromide, I'm going to say bromide, is equal to 2.77 plus 0.181 plus minus 5.28 iron. This is iron 1. This one has time on it. So we are going to put a big T there and also a big T here. Remember, in our data set, we coded bromide 1. Is that true? Let me look at the code. Yes, we coded bromide 1. Now, in this model you see here badly written, we are going to substitute where there's iron 1, we substitute with 1. So if we multiply here by 1, we are going to get a value of minus 5.28. Then rearrange our model. So our model now is going to be bromide. Let me use this one. Bromide is equal to 2.77 minus 5. Oh no, plus, not minus. When the negative crosses the equal sign, no, it has not crossed actually. Sorry about that. The negative hasn't crossed the equal sign, so it's still minus. Okay. Minus 2.8, then plus 0.181 time. Okay, so here we have two models. We have this one of rubidium, and we also have this one of bromide. The same slope, but different intercept. That's why we see in our scatter diagram that we had parallel lines. So those are the two lines we have. Okay, so you can actually put them on the model later on when you do your R script, but we won't do it now. So I just wanted to show you that if you have a categorical variable, you can actually run it using a dummy variable. And then you will need, if it becomes significant, you need two regression models. One where iron is 0 and one where iron is 1. I hope that is okay because I'm going to the next bit. Okay, so next, I want us to have a glimpse of polynomial regression. Okay, so in the chat, anybody who has a problem with what I've been saying? Okay. Okay, people don't have a problem. So let's go to polynomial regression. And remember, I am going to do a plot to show you the type of relationship you have. Then we decide whether we should have nonlinear regression, linear regression, etc. So the data set again is within your folder. What you do, just use line. In my script is line 16, but it reads hard as a function of had is equal to read.csv in bracket had. So that's what I'm running, and then view our data. So this data here, I'll give you a small background. It talks about making of paper, the paper we use for writing. What do they do in the industry? They collect wood, then disintegrate it in what we call pulp. And then the concentration of pulp, they add chemicals and make paper. Then they test the strength so that when you pour water, it doesn't get disintegrated. So here they were looking at different concentrations of pulp versus the strength of paper. Okay. So this is the data we have. Hardwood concentration versus the tensile strength of paper. So let's plot. Line 19 is a plot of tensile strength as a function of hardwood concentration. When you run that hardwood concentration as a function of, we get that. So what do we see in the chart? Let me see in the chart. What are you seeing? What are you seeing in the scatter diagram? Curve, linear, polynomial, a curve, okay? So we see a curve in this. Somebody says nonlinear mode. Okay, sigmoid curve, all that, okay. So here, inverted U, likely a probability curve. So here what we are seeing is a curvilinear relationship between tensile strength and hardwood concentration. So the first thing we are going to do is to run a linear regression, assuming we ignore the shape of the what? We ignore the shape of the model we see in the scatter diagram and run a linear relationship between tensile strength and hardwood concentration. What happens? So let's run. And there we go. So in the console, if you pay attention to hardwood concentration, you will see that actually the linear relationship is significant because the p-value is smaller than 0.05. Let's go down and look at the amount of variability explained. The R squared is 0.305, meaning 30% of the variation in tensile strength has been explained by hardwood concentration or by the regression onto hardwood concentration. So meaning there are other factors that are required in the model for us to be able to explain some of that variation. We can also draw, before we go ahead, let's construct our residual plots to see whether, even if the model is significant, are the residual plots telling us that the assumptions are not violated? So let's run line 24 and 25. So we run that, and we have the 4 plots. So I'm assuming that you're following. We've already done this. The only difference is that now we have data which is curvilinear. So when you run your residual versus fitted value, you can see that the residual is increasing with the fitted value. And we see that the residuals at the beginning here of the curve, which is pinkish, is smaller than the residuals on the other side. So it is also showing us that actually the linear model doesn't fit. That red curve is showing you that you need to fit a curve onto this data, not a linear relationship. When you go to the scale location, it's also telling us the same, that actually the linear model doesn't suit our data. You can see it is a curvature drawn in it. And also it is also showing us that we are likely to have some values which are outliers, which can be confirmed. When we go to the QQ plot, there is normality, but there are some variables down here. You see the points are lying on the dotted line, indicating that actually The data is normally distributed, but we have outliers here. There's outlier 19, outlier 18, and outlier 1. If you look at the QQ residual plot. In the Cook's distance plot, residual versus leverage, I don't know whether you can see it or I zoom in it, but it is showing that residual 19 might be an influential observation. Let's keep that for a moment and look at when we apply a quadratic regression, what happens? So we are going to run a quadratic regression. First of all, we have to create a variable that represents a quadratic variable, meaning that you have to multiply hardwood concentration by itself. You square it. So here I've created this variable and I'm calling it hardwood. The object is called hardwood. In hardwood, look for hardwood concentration and call it hardwood concentration 2. Assign a quadratic term on it. This is the line 28. So if we run line 28 and view, we shall see that in our new data set, we have a third variable called hardwood concentration 2. So we can X that out and run a model where we are going to have tensile strength as a function of hardwood concentration plus hardwood concentration squared. That is line 31. And when we run that and run our summary, we are going to see that hardwood concentration as a linear term is still significant, and even the quadratic term is also significant, meaning there is a significant quadratic relationship between tensile strength and hardwood concentration. Let's look at the R squared adjust. When you look at the R squared adjust, it has improved from what we saw before. Now we've explained 89.7% of the variability in tensile strength. We want us to look at the residual plots. You've already seen what happened. Now let's look at the residual plots with the new model. And we run and we see that, let me just zoom in and stop sharing and share the residual plots. And we see that we are doing a good job. Okay, ladies and gentlemen, this is the plot, which is zoomed in. Remember the graph we had here, it was showing that it was a curvature. But now we can see that the graph has improved. It's a random scatter of points, only that we still see some bit of curvature. And when we go here, it is still showing us there are some points that are likely to be influential. And when we go here in the QQ plot is telling us that our data is not normally distributed. You can see almost all the values are falling off the dotted line. When we go to the Cook's distance, there is observation 19, which is influencing the shape of the line. So what we could do if we had time, we could eliminate observation 19 and see what happens to our model. But still, when you look at our residual versus fitted value, we still see that there's a bit of, though it is a random scatter, but I think we can apply a cubic to the data and see how far we go. But still there's some improvement. That's what I can see. So I'll stop sharing and share the script. And that's all about quadratic. You can go ahead and run a cubic and see how it improves. But I think it is a better presentation compared to when we put in on a linear term. Although we see that there are some observations influencing the direction of the curvature. So we can remove them and see what happens to our parameters, the slope and intercept. So that is the polynomial regression. Apparently, I think we have how many minutes to go? We have only 8 minutes to go. And tomorrow, I want you people to be exposed to survey. How do we collect data in survey and some bit of analysis? So I beg to stop here. And if you want model building, please invite me to your university. I get a chance of seeing you face to face. But let's skip model building for the next session. It's also an interesting topic, model building. I love it because you're playing with numbers and seeing numbers, how numbers influence the biological system or the economic system. So, ladies and gentlemen, I would like to stop here. We cannot do any further, but I thank you for your patience. And in the last part, I was a bit fast. The speed governor button was not pressed, but I believe you've understood. Somebody saying, do you have nonparametric? Ladies and gentlemen, you see that we prepared a lot, but we can't cover everything in this short time. But thank you for being patient with me. And I hand you over to Forum. David, take over. I'm done. Unless if my colleagues, Helen and Thomas, do you have anything to say? They are saying they don't have anything to say, but you have been very excellent. I don't know whether that word is there, but excellent, more than excellent participants. Thank you so much. Thank you, thank you. And back to Forum. There you go. Okay.
Thank you so much, Prof, for being a very good teacher. Even Dr. Adon said he's not a teacher, but you people are doing so great. You've done so much, teaching people who are just coming from a no R background, but you really, I can see most of the people really understand now what they are doing and all that. Thank you so much, Professor Susan and your team. We really appreciate. Participants, thank you so much. As usual, we are really grateful. Please ensure that you have filled in the registration attendance, and also the materials for these trainings are all in that folder. I see we still have people who are asking for materials. Please, they are all in one folder, which was put there a week or 2 weeks ago. So thank you so much, Professor. Thank you so much, participants. We see you tomorrow again and wrap up our